Whereas for DecisionCAMP, it's not really aimed at people who have been using rule engines. It's aimed at people who are new to rule engines. So feel free to check your emails and do whatever you want to do. But if you don't have experience with rule engines, then you might enjoy this talk. So this is what I use to try and ease people into how a rule engine can work and learning how to use them. So when I first start off, I try to get people to understand, if you know SQL, a lot of people from business, from industry, they have SQL experience, and they don't understand what a rule engine is. So I said, well, if you know SQL, then you know a production rule engine. So I don't mean all rule engines, but they can get to understand how a production rule engine works. So I have an account, cash flow, and account periods, 3 tables, and there's your SQL. I want to select the credits for a certain date range. And then this is the rules. So where in SQL you have your tables, in a rule engine we have these rules, we have these objects you select from your account. There you have your account pattern. Same for the account period. And there's your cash flow, there's your type equals credit. The constraints are inside of the pattern, so they're outside with SQL, and that performs the join, and that's your date range. So just trying to get people to understand, if you understand SQL, actually I will go back, if you understand SQL, then you can understand rule engines. So this is selecting the rows of data, materializing them for the credits, materializing them for the debits. For each row of data, it executes a trigger, and that's the balance. And then the first 3 are what we call arbitrary. If I wanted to print the balance, we have to do that after we've done all the cash flows. So we use a thing called salience. We set it to a lower value. That means that we printed it after all the other ones. And then we increase the dates. For the next quarter, it does the 1 credit, and then the balance is done. So that's just to try to get people to understand the semantics of it. So we're going to start with the simplest example, which is number guess. So you have 5 out of 5 guesses, and please enter your guess from 0 to 25. So I put in 10. I got quite lucky, actually. I generally did manage to guess this the first time round. So I put in 10, 5, 2. You guessed correctly. So what does a game look like? So this is a Java-based system. This is your Java class. So we have the game. It has 3 fields, biggest, smallest, and guess count. You have the guess, which is the current value. The game rules, which is the maximum range, 0 to 25. The allowed numbers of guesses, 5. And the random number which it selects. This is just how we load and initialize a system within Drools. And now you can start to see the game. So the first one is, there we go. Yeah, so the first one is the main. So this initializes it. There is no guess. The user has not provided a guess. So it will set the focus to guess. That means it's going to allow the group of rules called guess to evaluate. And as you can see, there's the string you saw earlier on. The buffer reader allows it to open up for keyboard input, accepts the keyboard input, and then the input is passed, and it's inserted into the system as a guess. And then it will record the highest guess, and it will record the lowest guess if it matches. So it knows the last guess, and it will see if it's higher or lower. And if the guess is correct, it will tell you the guess correct. So yeah, your guess was too high, your guess was too low, you guessed correctly. And it will just use the loop around. So the previous one retracted the guess, which means it now loops back around again. So that's a very simple number guess game. It just goes round and round to either you run out of guesses or you guess correctly. So next one, get a bit more interesting now. I'm sure all of you who have a computer science background remember Wumpus World. So this is a cave-based game, and actually you don't actually see it. So I put a grid onto this so people could visualize what you're only supposed to get via sensors. And the game has a number of very basic rules. This is like one of the first things you learn in computer science. You have the performance measurements. So if you grab the gold, and you win 1,000. If you die, you lose 1,000. There's a cost of 1 per step and a cost of 10 for the arrow. Squares adjacent to the Wumpus, you get a signal saying it's smelly. So when you're running around the cave, all you get is sensors. And the idea is you have to navigate and try and win the game using these sensors, i.e. collect the gold and come up from the system. When you are next to a pit, it tells you that it's breezy. If you're on the same square as gold, it tells you it's glittering. If you shoot the Wumpus, you'll hear a scream. Shooting the Wimpus uses up 1 arrow. You can pick up the gold, get back to the beginning, releasing the gold. So climbing out wins. So this is basically the model. You have your cell, you have your hero, you have your Wimpus, pit, and gold. And everyone has a row and column. That's the cell within the grid that they live. So I'm just going to show you a little video now of this actually working. So this is a little animation that starts off. There's actually a client which you can program. And first of all, I'll show you this is how you should play it. So everything's switched off, and all you're going to see is sensors as you move around the system. There goes a breeze. So I know somewhere around me is a pit. A bump, that means I bumped into the wall. I might just hit the grid. There's back to another breeze, turning around, moving up. I walked into a pit. So I'm just going to play the game now. Restarting the system, but I'm going to cheat a little bit now. So I'm moving around, so it's showing me what I'm seeing, where I'm going. Just done the first row, haven't seen anything. I'm going to go up, and in a second it will give me, there you go, there's a stench. That means I know the Wimpus is around me. It sensed the items around me. So I've got to be careful now, I don't want to walk out. There's another stench. So I pretty much know that that is where the Wimpus is. I've just walked into the wall. I'm going to walk backwards in a second, and then you're going to see why. So when the up and down arrow key, all depend on how they work, depends on which way you're facing. I'll show you some rules to make you understand what I mean by that in a minute. There's the stench. So, I've walked all the way around the Wimpus now, going forward. There's a breeze. So somewhere there, I know there's a pit. Still trying to find the gold, looking around. Doing pretty well. I haven't died yet. There we go, got the gold. So grab the gold. Congratulations, you won. And I think I just showed dying now. I know you're into a pit. So you can see how the system works. And finally, we have a cheat button. There you go, it shows you everything. So for those that are lazy, you can just play it with the cheat button. Oh, I think another thing I'm going to show you, I'm going to shoot the Wimpus. So if you're facing the right direction, you get 1 arrow, you press shoot. There you go, you hear the scream. So if you hear the scream, you know you've got the Wimpus. I'm just going to kill myself now. There we go. You were killed by the pit. So I'm not going to explain how this whole game works, but I'm going to try and show you a little bit what these rules look like so you can try and understand how a rule-based system, remember this is a talk aimed at people who are new to rule-based systems, not that people have been doing it for 40 years, some of you. So remember I mentioned before, you're moving up and you're moving down. And how you move up and how you move down depends upon the direction you're facing. So this is a pattern matching system. And every time we're pressing one of the buttons, it creates a command. And the command tells the actor, the hero, what to do. And we have a different number of commands, but here we're looking at the move command. And it could be move forward or move backwards. And all depending on whether the direction is up or down depends upon how move forward works. Obviously, if I'm facing forward and I press forward, you move forward. But if I'm facing downwards and you press forward, then I actually go down one. So you can see the OR here. This allows me to have two different types of logic. These two rules, though, are mutually exclusive, so only one can fire. So it detects which way you're facing, which way you want to move, and then it's simply $H refers to the hero. It increases the row count, so that will move them +1. If it's going this way, it changes it to -1. The hidden bit is for the cell. You saw how it's grey first. As you walk through it, it's no longer hidden, it's no longer grey, so it changes that to false, and that's how it goes from grey to showing you the white cell. And it's the same when you want to turn left or turn right. Depending upon whether which way you're facing, depends upon what turn left or turn right means. So both these here, I'm turning left, but I'm facing up, turn left means left. But if I'm facing down, turn left means right. So this is the type of logic, actually, particularly the first one, a normal rule practitioner would do this wrong. They wouldn't realise the inversion of the logic, they wouldn't realise to use the OR, and they'd write the first type of system, and it would look like it had written the rules, when I move forward, go forward, and then they start to realise it doesn't work. but it looks like it's a literal translation of the rules we saw at the beginning. And that's a sort of mistake that first people make, is that they, particularly more sort of business analysts, don't quite have the logical brain to first time do this type of logic. Sorry if there are any business analysts here. But they do struggle with this type of stuff. Then I want to show you an invalid move. So an invalid move means you basically try to move to a cell that doesn't exist. So what I do is I'm actually checking that there is no cell for your particular direction. So it goes through all the different combinations of areas you could move to, and right at the very bottom it says fill bump. So if you can't move left, right, up or down, then it tells you to fill bump. And I don't know if you remember, when it reached the wall, you got the sensor fill bump. So the moment you insert that object, the sensor is displayed on the screen. So here we're using a reactive-based system that is reacting to commands to instruct it what to do. It's looking at the environment around it to move it around the system, and it's detecting when it can't move, and it's letting you know. Not only is it detecting when you are trying to move out of the grid, so it gives you the bump sensor. It can also tell you when you smell the stench. So if you look at the hero here, the smell stench, it gets the column and the row of the hero. I'll explain what this watch is in a moment. And it checks for all of the adjacent cells, above, below, left and right. Does the wumpus exist in that? If the wumpus exists, it logically inserts a smell stench. The reason why I say it's logically, because if you move one forward or you move one backwards, and you're no longer next to the wumpus, then it will automatically remove the sensor. So you don't need to check for when you're no longer around the wumpus, because you logically inserted this object. So this object, the smell stench, exists when this rule is true. If you move to a cell that you're no longer adjacent to the wumpus, therefore it's no longer true, therefore the object is retracted. So we're using logical assertions to be able to maintain the truth of the system so that our sensors are true based upon the data that we have. This little watch thing here is a way in which we control recursion. So you can control, by default, each of these patterns will listen on fields they constrain on. So if you change the row and you change the column, because we have constraints for those, it will react to them. But however, the hero is not constraining on anything. So as the hero moves, how do I get it to respond to those changes? So I'd say to it, even though you're not constraining on those, you're not listening on them, I want you to listen to them anyway. So we have the ability to say to the system, I want you to listen to row and column changes. This has the opposite side, that actually sometimes you don't want it to listen to. So you can say to it, don't listen, although you might be filtering on these certain fields, don't listen to their changes. And we can use this to control recursion within the system and to control reactivity. It's quite a powerful mechanism. We call it property reactive.
Mark?
Yes?
I have a question about this logical insert. So is that done when one of these places becomes false?
So this rule, if the hero is next to the wumpus, it will create a rule instantiation for that. That rule instantiation will exist as long as the data is true. If the ground term...
View, right? It's like a view in the...
Yeah, it's a materialized view. So all production rule systems, you just saw in the first examples, is a materialized view. And as long as the row exists, the row of data, the rule instantiation exists, the logical object will exist. If the ground terms of the underlying data changes, and that row is removed in a materialized set, the row is no longer supported, it's deleted, it has a reference to all those logical insertions. Those logical insertions are also deleted. Okay. Here we're detecting death and pip death. And again, it's very simple. It's just correlating on the row and columns where the hero is and where these other objects are. The last one that's quite interesting is the shoot arrows. You saw the direction you're facing. I can press a command that says I want to shoot this arrow. So we know when this pattern is matched, the user has pressed the shoot command button. We have to make sure the hero has at least one arrow. Well, we know that they only have one, so it's 1 or 0. So we retract the command. We set the arrows to 0, so they can no longer fire any more arrows. And then we insert the arrow with a direction. the arrow direction is the direction of the hero, and we change the focus to shoot. The focus means the group of rules that's allowed to fire. So obviously here we're in the command group, we're evaluating the commands. So there are several rules within the shoot group. Move arrow up, move arrow down, move arrow left. I didn't copy all of them. Up here you can see the shoot arrow. And this will work recursively because it's modifying the arrow continuously. So what this will do is, where is it? There we go. This will continuously increase the row +1, or the row -1, or the column -1, so the arrow will iterate through each of the cells. The process of modifying causes it to recurse, so it will keep going through. Once it gets to a point where there is no row or column, there's no matching cell, it will actually retract the arrow. So it means when you press the word arrow, it will find one particular rule that matches a direction, and that will increment the row or column until it gets to the boundary. And or it may get to the whimpers. So as the arrow goes through, we check if the arrow is on the same row and column as the whimpers. If it does, then it emits the here screen and modifies the whimpers as false. And that's where you saw the graphic change. And that's that. That's the classical whimpers world. If you were to use this within rules, there is actually two files. One is the game that runs the game, and the other one is effectively the client. And you can program the client to try and get it to issue commands, to listen to sensors, and to try and get it to solve the problem automatically. So there is, if you are teaching computer science, you can download this example, you can give it to your students, and they have an empty, that it will run, and they can use the UI to go through it, and the client side is empty, and they can just start putting in rules in there and running it and seeing if they automate. So that is ready to go as a student teaching exercise. Right, the next one is, does anyone here know AMSI, Adventures in Prologue? Everyone must know that, right? Yeah, cool. So I started off in production rules, and I really didn't understand Prologue. I'd come along to RuleML, and I'd hear the descriptions of it, and backtracking, and cutting, and I really didn't get it. The only time I got it was I sat down with the AMSI Adventures in Prologue, and I went through all of the exercises in there, and that's the first time I truly understood it and truly understood unification. Anyway, so I've done it's not an exact copy, but I've done a version of this in rules, and again, it's a nice way to teach people to understand rule chaining, reactivity. This now will combine both reactive rules with some little bit of queries to help people understand, and I've introduced some very basic transitive closures to introduce more advanced concepts to people. Let's just put the video on. Sorry, let's try and enlarge that. Okay, so you start off, and I'm just going to move into the kitchen. I try and move into the basement, and it says the basement door is locked. So I go back and go into the ground floor. I'm going to the lounge. I'm going to pick up the umbrella. It's very important to have the umbrella. It might save your life one day. So I'm going back to the ground hallway. I'm obviously trying to find the key. Go upstairs. I go into the office. In the office, there is a desk. So I try and pick up the desk. You can't pick up the desk. So I search the desk. There's an envelope in the drawer. The drawer is in the desk, and the key is in the envelope. So I tell it to pick up the key. You have the basement key. So now I can go back to the door. So it's just going all the way back downstairs again. Trying to get to the basement, so I've opened the key. I go into the basement, and there you can see there's a monster there. And actually I can play both characters. I'm going to switch to the monster now, and characters can give each other things. Going back again, notice how it changes what each character can see. And I'm going to give the key to the monster, because I'm nice, so he doesn't get locked in the basement again. I go back to the hero, and I'm just, so the monster can see the hero, just showing the monster moving out of the kitchen. I mean, the door was unlocked, so he could move out anyway. The hero's going to chase him, decided he doesn't like him after all. It's just showing that the state changes, the look states based on the character. So I go out to the kitchen, I can see the monster again. So I use the umbrella on the monster, and you killed the monster. So that's it. The monster's dead. I'm going to show you a little bit now how you build a game like this. I used a scripting language called Enval. It's just a lightweight Java expression language to be able to build data structures. So I've got my rooms, basement, lounge, dining room, and I have my doors. Notice the doors only point one direction, so I don't have to do them bi-directionally. I'll explain why in a moment. So I define all my doors to connect to my rooms. I define my hero and my monster. I define my items, my umbrella, my desk, my drawer, my envelope, my key. I define the locations. Notice the key is in the envelope. So there, the key is in the envelope is in the drawer is in the desk is in the office. And the office itself is a room, which is connected by a door. Let's start with the look command. So, remember I mentioned before, we have these groups, so obviously I'm at the stage of the game where I am evaluating the command that's come in. The command is look. And I have the location of the character. So I want the location of the character. So this is the joining. So when I say the look command, it's the look command for the current character. That's how it switches between the monster and the hero. For that current character, I want to get its location. And you see this thing here? That means it's going to actually call a query. The apostrophe means that the query will not be left open. It means I want the results, and then it can be closed. It will not be a reactive query. I will try and explain that with an example in a minute. And it just prints out the results. And that's what you were seeing as I was moving through the system. And this is the query. So there is a character, and it's going to return a list of things, exits. So here we have a basic unification because the input variable is C as the character, but things and exits have not been defined yet, so those are output variables. So there's my character. It will unify against that. And then things and exits are also two additional queries. So if I go to the things query, Accumulator allows me to accumulate a set of results. So it's going to accumulate the location of everything, everything except the character, because obviously the character is in the room, but I don't want to put that into my list of available things. And I want my list of exits. Remember I said that you don't have to define doors both ways, because I want my connect. So that's actually another query, which I show on the next page. Here we go. So when I collect the results of connect, it's showing door XY and door YX. So it will check both ways using OR to be able to see, to be able to list my available exits. So let's get on to the move command. As you've seen how I can look at my environment, I can get the information back, and how I can use a number of queries that call a number of queries to provide that information. So the move command again, there's the move command there. There's my location. See there, I don't want it to watch the target, and that's because I modify the target field. If I did not have the @do not watch, it would go into an infinite loop. So I have ability to control the recursion and the monitoring of my rules. I just emit events there because I want to be able to monitor the events. And what this does here is I want to be able to just, the feedback you saw on the page, letting you know that you've moved. The connect there, if you remember, that's the connect that returns the door. So you have to have moved to R, which is comes from the move command, and that connection, that door, has to exist for you to move through it. I can extend this. So this is the move command. I can extend this. So locked extends move, because I want to be able to handle locked doors. So the D variable was bound in the previous one up here. So D is the output door. So if there is a valid door, it will be returned there as an output variable. That D is now available to be used as a pattern, and I want to say, is the door status locked? If it is, then output the door is locked. So I actually have two rules here. One extends the other, adding additional logic to be able to handle different cases. I'm going to show you another way in which you can handle different logic. The other one was doing extends. This one is using conditional branches within the pattern matching. So this is for unlocking a door. I've said I want to use the key with the door, and it's getting the room, the location, checking if there actually there is a door for that location, and then it says if the door, it's making sure that the thing is the door. Am I using the right key with the right door? If I'm not, then it's the wrong key. Then it's checking to make sure it's unlocked. If it's not unlocked, then I'm already locked. So this allows me to call three different consequences, or three different sets of actions, depending upon the if. The break keyword there means do not go any further in the pattern matching. So if this one is true, the second one will never be, or anything below that will never be evaluated. Likewise, if either of these are true, the break means that the default then will never be executed either. So you can use this to have some sort of, it's equivalent to having three different rules. But you can end up with a rule explosion can make it very hard to read. So on one hand, it's a little bit more complicated, and people might say, well, if I saw three separate rules, I could understand what they mean. But actually, when you have 100 rules in a file, you start to appreciate reducing the number of rules and realizing that they have shared logic. So it's a little bit similar to the extends, but it's just another way of expressing that within a single rule file. So this is the last bit. Within the UI, you saw how the different UI elements, your exits and the things, was updated as you move from room to room. The UI is automatically updated. And the way that works is I have some rules set up. Update things, update exits, and each time the user's location changes, they return a new set of things or a new set of exits. These are things as a query, if you remember, exits as a query. But notice they don't have an apostrophe on it, so a question mark. Before you saw a question mark, which meant that the query was non-reactive. The data could change, but you'd get no more reactivity. The question mark is not there, which means that actually as the character's location changes, that query will now be reactive. Every time it reacts, it's returning a collection. This channel allows me to send information to the UI, and the UI will display the results of the things, display the results of the exits. So that's a really nice way to have the reactive system and the query system, the optionally reactive query system, update the UI as you move around. And you already saw these already. The same queries I just shown to you before. They were used in the look command, so we've already been over those. You saw that with the desk is in the office, but it's got the drawer and the envelope. And how did I search that? So we have this thing called is contained in, and this is what's called it's a special type of query with a transitive closure. So I want to search the desk. And this desk will go down the chain of stuff and return all of the children. I want to know the children, and I want to know the parents of the child that it gets to, because I want to be able to, I'm going to collect this twice. The first time as a string. I want to know which the envelope, the key was in the envelope was in the desk, the envelope was in the drawer was in the desk. So I need to print that out for output. But I also need to collect the child, because the child is sent to the UI there. Because as I've searched, I want to display the search results. So this is how I'm using a transitive closure to get a nice string message and to update the UI for me to pick my items. Almost everyone here knows what a transitive closure is. So this talk is aimed at people who are new to rules, don't have an academic background, they are practitioners or possibly first-year graduates. So this is how I would explain what a transitive closure is to people. So again, feel free to check your emails, to do whatever you do if you know all of this. So here's my is contained in. I don't have the R in there, so this is the parent, because this is a simplified version. And what this is saying is X contained in Y. And it will check to see if there is a location object, a ground term, where X and Y match. If that does not match, it will then notice the Z there. So it will say, is Z contained in Y? Z is unbound, so it's going to find all the things that are a child of Y, and then it will call is contained in recursively, except now Z, which before was a child, now becomes the parent. X now will be bound to all of the children of Z. So it uses this to recurse down the system. I insert my graph. It's not exactly the same as the one you saw earlier, but it's the graph that matches this here. It's a simplified version of what's in the game. I have a rule, and I just want to print every string so I can see what's going on within the system. And go1 will simply say, is the office in the house? Here's a reminder of the is contained in query. And if I insert go, type file rules, go1, it will print out go1 because that is the rule that matches that and outputs it. And it will say the office is in the house because that also matched and fired. Very, very simple. So that would have matched straight away this pattern here because there's a ground term for the two input arguments I was asking. Yeah, so there we go. There's the ground. It goes straight. The is contained in query goes straight to the ground term. So now it's going to say, is the drawer in the house? So there's the query. Insert go2. And it says, yes, the drawer is in the house. So how does this work? It calls is contained in. It says, is the office in the house? Because, first when it tries, is the drawer in the house? There is no ground term for that. So then it tries the location ZY. It gets all of the children of the house. We know that office is a child, and we know that kitchen is a child. And then it will recursively ask that. So it's asking, is the drawer in the office? And we know that it is. But it also asks, is the drawer in the kitchen? Because it's going to go down both sides. It doesn't yet know that the drawer is in the office. So it has to go down both sides. But obviously we know one side will fail. Is the drawer in the office? Is the desk in the office? Is the drawer in the desk? And yes. There we go. We know there's a ground term for that. So that's how it recurses down. I didn't go down the branch that it would have failed. I think it was fairly obvious. So now I want to say is the key in the office. So this is the same thing. It's just going to go down an extra. I'm starting at a different point. Whereas before I started in the house, now I'm starting at the office. But it's effectively the same thing. I'm going to go through that quickly. This time it's different. I'm asking it, thing is unbound, so it's an output variable. Office is an inbound variable. So this is going to basically return all of the recursive children of office. And again, remember, I start off, people who come to this talk will know SQL. And I'm trying to get them to understand a rule is like SQL, but it can do many things that SQL can't. And its ability to have input and output variables is something that an SQL query or a materialized view cannot do. These are the advantages that a rule-based system that offers unification has, this ability to recurse over graph relationships in a very compact syntax. At least standard. SQL's found other ways to do similar things, but not quite the same way. So it says here this is an output variable. It says go for, and it will say the key is in the office, the computer is in the office, the drawer, desk, and chair is in the office. Now they're both output variables. So it's going to find everything in everything. Okay, how long do I have left?
What if you have a cycle evacuation?
Yeah, we don't do, it will go off forever and blow up. So we don't do recursion control. Okay, this is really, really quick. I might be like 3-4 minutes if that's all. Yeah. Oh, I should have played. Oh, sorry. There we go. So this is just a simple Space Invaders game. You can key control left, key control right, end fires a missile, and there's collision detection. That's the end of the game. The reason I want to talk about this one is a nice one to introduce the idea of a game loop and how we can use rules to control the flow of what we're doing. So it starts off with the init, it checks the keys, it does the move, it fires the bullet, which also checks collision detection, and then it will draw that on the screen. So here's the rules for the key press system. They come in on a stream. So I'm basically saying that these patterns are coming from particular streams. And all it's doing is, if you hold down the button, it can emit lots and lots and lots of events. This is just logic to be able to say, I only want the first one, ignore the other ones. And then it will input into the system which key was actually pressed, not all 1,000 events that were key events that were fired. So that was the keys. So it will say whether the Z, X, or M key. Sorry, it doesn't actually. It detects. It gets the key press. Now we've got the key press. We need to be able to do something with it. So that was the keys group. Now in the game loop, it goes on to the move. So the move will see whether it's Z, X, but as well, it knows if you had Z before, it needs to know when Z is no longer pressed. So it changes the delta, which is the speed. So if you press Z, the delta is 0 minus the speed. If you were to press X, then the delta is 0 plus the speed. When you no longer press it, it detects that and sets the speed to 0. Notice this one here has the keyword run. I'll explain this in a moment. It also has the word not X, not watch X, because I'm modifying X, I don't want that to recurse. But as you move, I'm holding down the button, the key. Once the delta has been changed, it will not change again. And I'm not watching X to change. But clearly, every game loop, I need this rule to fire. So that's what this run does here. Every time the game loop gets to the end, I say update run. So every rule that has the word run in it will fire the consequence again. So even though the pattern that matches this one here that doesn't match, it was matching before and continues to match, because the run is updated, as I've said to rematerialize its rule, that will continuously fire to increase the X. This is now the bullet one. So it's the same thing. If I fire, if there's no bullet, create the bullet. It just sets the location, and it will modify the bullet. Y equals Y plus 1. So this is see the run again. So every time it goes through the game loop, even though I'm not detecting Y here, so it's not the change of Y which causes the recursion. It's the game loop and the fact that run is called update. So every time it goes through the game loop, the Y will be increased. But that rule doesn't recurse because I told it not to watch for Y changes. If the bullet overlaps with an invader, then it will set the invader alive to false. This is the drawing. So this starts off, when it says to draw, it will clear the canvas, it will draw the ship, and then draw the invader. Notice again I've got the run there, and that game makes sure that every game loop the invader is drawn. Let me just go back to the... Oh, I didn't include it. Oh, it doesn't matter. I was going to show you how you program the game loop, but I missed that one. Apologies. Okay, finished. So I think for people who haven't used rule-based systems before, that are trying to understand in a reactive system, the difficulties of dealing with control loops, dealing with how we orchestrate our rules, how we solve real, how you build up the skills to solve real problems. So obviously I'm not saying that rules are a great thing for building computer games. It's not. Actually, it's really inefficient compared to imperative code. But I even learn because I find out all the problems with rules is very difficult to solve these problems. That gives me roadmaps of features we need to improve. So it allows me personally to focus on the programming model, to focus on how to improve the language, to make those games easier to write. And it allows new people to learn the techniques necessary to solve their problems. It makes their brain think about the control, the execution flow, recursion, and how these things interact with each other by changing states, not by imperatively saying do this now, other than the very basic game flow. I guess no questions, right? Cool. I'm done.
Very interesting. About one of the two possible applications, when you say for some people who maybe don't have that logical mind,
Yeah.
There is an example, not on a classical game, but it's a modern video game. It's a small one, which is called Human Resource Machine.
Mm-hmm.
I don't know if you know about that.
I don't know that one.
Yeah. Because it's a small game where you have to program an employee to change value of boxes from source to out.
Yeah.
And you can only use a limited set of rules and a lot of breaks or loops and so on. So actually it allows to teach some of these things with a more complete interface. But just to say that this is, I think it's very interesting direction for teaching this kind of basic.
I've done a different talk where I go through Pong, and I say, well, these are and I build Pong in 10 minutes, and I put down the business rules of Pong. And the idea is, I often say, it would be a very great exercise to see if you were to have a developer not try and preempt things, but to only do what the business analyst was saying, could they actually build Pong? Looking at the rules, or would the business analyst be able to describe the execution rules? It'd be an interesting exercise. You don't want the developer to carry the business analyst. You want the business analyst to realise the translation problems, such as you saw with the move up and move down. If the developer was to do a literal translation of the business requirements, it wouldn't work. Could you get the business analyst to recognise that and preempt it and do it first? Without, so often developers will carry the business analyst to make them not have to think about those types of things.
Gamification of the process itself instead of being this game creation process. Gamifying inside the game, this creator could be even more entertaining for people who have to be taught.
Yeah, it could be used. I have thought about this as an exercise to get developers and business analysts to work together. It would be maybe one day I'll sit down and try and figure out how to get a teaching course around that, and so it'd be more about teaching the business analysts than it is for the developers. Okay, thank you very much, everyone.